Hello and welcome to this class on matrix algebra. Today we are going to cover the topics of your MSc syllabus, that is Hermitian matrix, unitary matrix, then eigenvalues, eigenvectors. We have to prove the Cayley-Hamilton theorem, and last of all I will explain you to diagonalize a matrix, that is the diagonalization process. So let's start with the Hamiltonian so let's start with the Hermitian matrix. So any matrix A, or rather it can be said as any square matrix A, is said to be Hermitian if the matrix A coincides with its conjugate transpose. For any square matrix A, if the conjugate transpose, that is if A dagger coincides with A, then the matrix A is said to be a Hermitian matrix. So here I have used three different terms. One is a square matrix, then the other is conjugate transpose. So there are two terms, one is the conjugate and the other is the transpose. I think most of you must know these terms, but I should explain this in a very short time. That is, if any matrix has equal number of rows and columns, then those type of matrices are known as square matrix. So a n cross n matrix, that is a 3 cross 3 or a 4 cross 4 or a 2 cross 2 matrix, is a square matrix. So this is the definition of a square matrix. And if you find any matrix beyond this definition, that it has less number of columns or less number of rows than the columns, then that type of matrices are known as rectangular matrix. So there are two types of basically matrices. One is a square matrix and the other is a rectangular matrix. As in a square matrix, you will find equal number of rows and columns. Now this definition of Hermitian matrix is actually taking into consideration a square matrix. So this is a square matrix. Now what is the conjugate of a matrix, or rather let us find what is the transpose of a matrix. So to find the transpose of a matrix, actually we write it as AT, that is the transpose of a matrix. So to get the transpose of a matrix, we have to orient, or we have to interchange rows into columns. So whenever rows of a matrix are converted into its column, then that matrix is known as the transpose of the main matrix A. So this is the transpose. Now what is the conjugate? As you know that if a matrix is an imaginary matrix, that is if the terms of a matrix is not real but imaginary, then you can find out the conjugate of those terms. So conjugate of a matrix, actually it is represented by A star. It is represented by A star, and this A star, to find this conjugate of a matrix, you have to find out the complex conjugate of each and every elemental terms of the matrix. Now let's find out, or let's return to the Hermitian matrix, that is the definition of a Hermitian matrix. Now this is the A dagger. A dagger actually represents the conjugate transpose. Actually, so if A dagger that is A dagger. A dagger means what is A dagger? In terms of AT and A star, A dagger can be written as A transpose and then its conjugate. So in many books it can be written as AT star, or the main operation is the conjugate transpose. Transpose means AT, and then you have to find out the conjugate of that transpose matrix, and that will give you the A dagger or the conjugate transpose of A. Now for a matrix A to be Hermitian, this conjugate transpose, that is A dagger, should be equals to, or it should coincide with the matrix A. Now if it doesn't, that is if there are many matrices which do not follow this particular law or this particular form, now they are known as the skew Hermitian matrices. So this is the definition of a Hermitian matrix in which A equals to A dagger, and for a skew Hermitian matrix it can be written as A dagger equals to minus of A. A dagger equals to minus of A, and those matrices are known as the skew Hermitian matrices. So this is the definition for Hermitian matrix, and this is for the skew Hermitian matrix. Now, if a matrix is real matrix, that is, if the elements of the matrix A are not imaginary but they are real, so what happens? So for a real matrix, actually you can't find out the conjugate. You can't find out the conjugate because every term is a real term. So that's why then the definition just transforms into A dagger equals to AT, that is the transpose of the matrix is actually equals to the dagger matrix. So you have to find out that A transpose, that is A transpose, then A transpose equals to actually A star, because the matrix is a real one. Okay, since the matrix is a real matrix, then A transpose is actually equals to A star. Now a square matrix, for the same thing happen for a skew Hermitian square matrix. If the matrix is a real one, then A transpose equals to minus of A star. So this is the definition of a Hermitian matrix. Actually you have to remember the general form, that is whenever A dagger, that is conjugate transpose of A, coincides with the original matrix A, then the matrix is known as a Hermitian matrix. Or if the conjugate transpose of A coincides with minus A, then the matrix is a skew Hermitian matrix. Now let's prove, let's move on to some basic problems. First of all, in this problem, I'm going to show you that every square matrix A can be uniquely expressed. Every square matrix A can be uniquely expressed as the sum of a Hermitian and a skew Hermitian matrix. So here in this sum, or here in this problem, we are expressing A, that is any square matrix A, equals to half of A plus A dagger, that is the sum of a Hermitian and a skew Hermitian matrix. So I am writing A equals to half of A plus A dagger plus half of A minus A dagger. As you can see that here half of A means A, and half of A dagger minus of half of A dagger, it will cancel each other. So in the left hand side I have written A, in the right hand side I have also written A. Now here half of A plus A dagger it can be written as P, and half of A minus A dagger can be expressed as Q. So here I've written P equals to half of A plus A dagger and Q equals to half of A minus of A dagger. Now let's find out P dagger. What will be P dagger? So that is half A plus A dagger, A plus A dagger, whole dagger. And that means it will be half A dagger, it will be half A dagger plus A dagger whole dagger. That is, it will be half A plus A dagger plus A, or it can be written as half of A plus A dagger, and that is nothing but that is equals to P. So from this we can explain that P is Hermitian, as because P dagger equals to P. So here we can express that P is a Hermitian matrix. Now let's move on to Q. Again, find out what will be the value of Q dagger. So expressing in the same way, that is half of A minus A dagger whole dagger, it will be half of A dagger minus of A dagger whole dagger, that is A, or it can be written as minus of half A minus A dagger, and that is nothing but minus of Q. So here you can see that in this step I have found Q dagger equals to minus of Q, and that will show that Q is a skew Hermitian matrix. So in the problem it was given that every square matrix A can be uniquely expressed as the sum of a Hermitian and a skew Hermitian matrix, and I have shown that P is a Hermitian matrix whereas Q is a skew Hermitian matrix. So my problem is solved. Okay. Now next move on to our second problem. The second problem says that if A and B are Hermitian, then show that AB plus BA, is Hermitian and AB minus BA is skew Hermitian. So in this problem, here A and B are Hermitian. It is given that A and B are Hermitian, and we have to show that AB plus BA is Hermitian. We have to show that AB plus BA is Hermitian and AB minus BA is skew Hermitian. So this we have to show that AB plus BA is Hermitian whereas AB minus BA is skew Hermitian. Now as we have given that A and B are Hermitian matrices, that means A dagger equals to A and B dagger is also equals to B. These are given. So therefore AB plus BA. Let's find out AB plus BA whole dagger. So it will be AB whole dagger plus BA whole dagger. Now AB whole dagger means it will be B dagger A dagger, as because the conjugate transpose. So it will be B dagger A dagger plus A dagger B dagger. And now since B dagger equals to B, A dagger equals to A, it will be BA plus AB, or it can be written as AB plus BA. So AB plus BA whole dagger equals to AB plus BA, and it will show that AB plus BA is a Hermitian matrix. Okay? Now let's find out whether AB minus BA is a skew Hermitian matrix. So to find out AB minus BA is a skew Hermitian matrix, we have to find out again AB minus BA whole dagger. That will be AB whole dagger minus BA whole dagger, and as whole dagger means it is the conjugate transpose, so it will be B dagger A dagger minus A dagger B dagger. Now B dagger means B, A dagger means A, and this is also BA minus AB, and it can be written as minus of AB minus BA, minus of AB minus BA. So it will prove that AB minus BA is a skew Hermitian matrix. Okay? If you have any queries, have you got it? If you have any queries, please write in the comment box to let me know. I think it is okay till now. Okay, so let's move on to the next problem. That is problem number 3. So let's move on to the next problem. That is problem number 3. And so in this problem, that is in problem 3, we are going to show that for every Hermitian matrix A, for every Hermitian matrix A can be expressed as B plus IC. That means A can be expressed as B plus IC, where B is real and symmetric and C is real and skew symmetric. Okay. So what is a symmetric matrix? Symmetric matrix means whenever the transpose of a matrix gives, or the whenever the transpose of a matrix coincides with the original matrix, that is B transpose equals to B. Here in this problem, what we are given that B and C are real, and again B is real and symmetric. So B transpose, actually as B is a symmetric matrix, so we can write B transpose, B transpose or B dagger. It can be written as B dagger equals to B transpose. But since C is a skew symmetric matrix, that means C dagger equals to, now as B and C are real, that means B dagger equals to B transpose and C dagger equals to C transpose. Now here that is also given that B is symmetric. So for a symmetric matrix, transpose of any matrix coincides with the original matrix. So as B is a symmetric matrix, that gives us that B transpose equals to B. But since C is a skew symmetric matrix, that means C transpose equals to minus of C. That means we get B dagger equals to B and C dagger equals to minus of C. Okay. Now let's find out A equals to B plus IC. So if A can be written as B plus IC, that means A dagger can be written as B plus IC whole dagger. It will give us B dagger and then the conjugate transpose. So it will be minus I C dagger. Okay. Since it is the conjugate transpose, it will give us B dagger minus I C dagger. And since B dagger equals to B, as B is real and symmetric matrix, wherever C dagger equals to minus of C, because C is real but it is a skew symmetric matrix, so it will give us plus IC. So A dagger equals to B plus IC, and that is the value of A, as because A can be written as B plus IC. So here it proves that A is Hermitian. Okay. So this is all about Hermitian, skew Hermitian matrix. So here up to this, we have already encountered some terms, that is what is a square matrix, what is the conjugate of a matrix, how you can find the transpose of a matrix, what is a Hermitian matrix, what is a skew Hermitian matrix, and in this problem we have found two other things, that is the symmetric matrix and a skew symmetric matrix. Now let's move on to a unitary matrix. Let's move on to a unitary matrix. Now a square matrix A is said to be a unitary matrix. A square matrix A having its elements as complex numbers. A square matrix A having its elements complex numbers is said to be unitary if A dagger multiplied with A gives us a unit matrix. So if A dagger A gives us a unit matrix I, then A is a unitary matrix. So the definition of unitary matrix is a square matrix A having complex numbers as its elements is said to be unitary if it can be written as A dagger A equals to I. If A is real, if the matrix A is real, then the matrix will be unitary. That means if A transpose A equals to I. So for a real matrix to be unitary, it will be the form, this form gives us A transpose A equals to I. So this is for any real matrix to be unitary, and this is a complex matrix to be unitary. So this is the unitary matrix. Now let's move on to an important topic of your syllabus, that is eigenvalues and eigenvectors, or rather I think first of all we should go for Cayley-Hamilton theorem. Now this is an important topic, that is Cayley-Hamilton theorem. Now for this Cayley-Hamilton theorem to discuss, first of all we have to explain again two definitions, or we have to know two terms. One is the characteristic matrix and then the characteristic equation. So now we are going to discuss Cayley-Hamilton theorem, and to discuss the theorem, let's find out two terms. One is a characteristic matrix and the other is characteristic equation. Now, if A be any n numbered matrix, n rowed matrix, and if I be an n rowed unit matrix, if A be any n rowed matrix and I be any n rowed unit matrix, then the matrix polynomial A minus xi, A minus xi of the first degree is said to be the characteristic matrix of A. And here comes the characteristic equation. So the determinant of A minus xi equals to 0, and this equation is said to be the characteristic equation. Determinant of A minus xi, determinant of A minus xi equals to 0 is known as the characteristic equation of a matrix. So this is the characteristic matrix. Now let's move on to the Cayley-Hamilton theorem. Now in this theorem, before going to this theorem, every square matrix A must satisfy its own characteristic equation. That is, if determinant A minus xi, if determinant of A minus xi can be written as A0 plus A1 x plus A2 x square plus An x to the power n equals to 0. Every square matrix satisfies its own characteristic equation. That is, if determinant of A minus xi equals to A0 plus A1x plus A2x square plus dot dot up to An x to the power n equals to 0 be the characteristic equation of a square matrix A, then A0i plus A1 A1a plus A2 s square plus dot dot An a to the power n equals to 0, where every x, just look at this, every x has been replaced by A. X has been replaced by A, so x square has been replaced by s square, x to the power n has been replaced by A to the power n, and for A0, now here A0, it can be written as A0 x to the power 0. Okay, now x to the power 0, then A0 into A to the power 0, and that is A0 into 1, that is, it can be written as A0i. So here A0 is written as A0i. So here every x has been replaced by A, and so determinant A minus xi, it transforms to A0i plus A1a plus A2s square up to An a to the power n equals to 0. This is the expression of Cayley-Hamilton theorem. Now here in our examinations, regarding this Cayley-Hamilton theorem, some problems can be given, and these problems are in this form. It may be in this form that you have given any matrix A, then you have been asked that find the characteristic equation and verify Cayley-Hamilton theorem. So you have to find out first of all the characteristic equation for that particular given matrix A. So you have to find out firstly the characteristic equation for the matrix, and then to verify Cayley-Hamilton theorem, every x terms must be replaced by capital A, that is the original matrix. So if the characteristic equation have x cube, you have to write it as a cube. If the characteristic equation has x square, you have to write it as a square. And then you have to prove this equation, or to verify Cayley-Hamilton theorem, you have to find out that value equals to 0. And after that, you can write that, so Cayley-Hamilton theorem is verified. Let's have a problem to check it out, how it can be done. So this is an example. So if the question is that find the characteristic equation of the matrix A, and this matrix A is given as, say for example, 1 2 3, 2 minus 1 1, 3 1 1. So the question is find the characteristic equation of the matrix A and then verify the Cayley-Hamilton theorem. As I told that we have to firstly find out the characteristic equation, and to find the characteristic equation we have to write mod of, or determinant of, A minus xi equals to 0. So the characteristic equation is determinant of A minus x of I equals to 0. So we have to write A, that is 1 2 3, 2 minus 1 1, 3 1 1, minus xi, that is I means 1 0 0 0 1 0 0 0 1. So this is A minus xi. So you can write it as x 0 0 0 x 0 0 0 x, and then after subtracting it will be 1 minus x, this is the first term, then 2 3 2, then the second term will be minus 1 minus of x, minus 1 minus of x, 1 3 1, and this will be 1 minus x, it will be equated to 0. Now you have to simplify, just you have to find out the determinant value of this matrix by simple algebraic manipulations, and you will find it as x cube, and it will be x cube minus x square plus 15x plus 15 equals to 0. Just few steps from here and you will be here, that is x cube minus x square plus 15x plus 15 equals to 0, and this is the characteristic equation. So first part of our problem, that is we have to find out the characteristic equation for A, and this is already done. Now the second part, that is how to verify that Cayley-Hamilton theorem. Now as I have told you earlier, from the Cayley-Hamilton theorem expression, that is you have to replace all x's by capital A. So to verify Cayley-Hamilton theorem, you have to prove x cube means a cube, you have to prove a cube minus a square, so this is in respect to x square, plus 15a and then plus 15i equals to 0. So you have to verify this, that a cube minus a square plus 15a plus 15i equals to 0. So it is a laborious problem, I think, as because you have to find out a square, then you have to find out the a cube, and after that substituting the values of a cube, a square, a in this equation, you will get a cube minus a square plus 15a plus 15i equals to 0, and after that only one step is required. You have to write that, so Cayley-Hamilton theorem is verified. So this is the process you have to follow for or to verify Cayley-Hamilton theorem. I think till now this is all clear for you. If you have any queries regarding Cayley-Hamilton theorem, please let me know, or otherwise I will move on to the next part. If you have any queries, all clear? Okay, Mrinal, Urpita. Okay, fine. So let's move on to the next topic, that is again a simple definition for unitary transformation. Now, what is unitary transformation? Now, if capital A be a unitary transformation of order n cross n, if capital A be a unitary transformation of order n cross n, and x, capital X, small x are column vectors of order n cross 1, then the linear transformation capital X equals to capital A into X is known as unitary transformation. This is just a definition. This is just a definition of unitary transformation. Now, since A dagger A equals to A dagger equals to I, that means X dagger X, it will give us, as X equals to A into X, it will give AX dagger with AX, and it will be X dagger A dagger and then AX. So A dagger A means 1, so it will be, since A dagger A equals to 1 means the unit matrix, so we have X dagger X. So capital X dagger X will be equals to small x dagger X, and it is due to the unitary transformation. Okay, so let's move on to an important topic of matrix, and this is the eigenvalue and eigenvector. And for eigenvalue and eigenvector, a non-zero vector capital X, a non-zero vector capital X, is called a characteristic vector. A non-zero vector capital X is called a characteristic vector of a matrix A. A non-zero vector capital X is called a characteristic vector of a matrix A if there is a number, lambda, such that A capital X is equals to lambda capital X. If this can be written where lambda is a number or it is a constant and capital X is a non-zero vector. So if Ax equals to lambda x, then this lambda is known as the characteristic root. Then lambda is called the characteristic root of A corresponding to the characteristic vector capital X. So here lambda is called the characteristic root and capital X is the characteristic vector. Now these characteristic roots are actually known as eigenvalues and characteristic vectors are called eigenvectors. So this is the eigenvalue equation. As we all know in quantum mechanics, this is known as the eigenvalue equation. But in matrices, this is from where eigenvalue equations are taken for quantum mechanics to use. Now this is the eigenvalue equation where lambda is the characteristic roots of this matrix A, or rather lambda is the characteristic roots corresponding to eigenvector capital X. Now so we have Ax equals to lambda x, or it can be written as lambda into capital I into x. Normally capital I is the unit matrix, and that's why it can be written as Ax minus lambda I x equals to 0, or it can be written as A minus lambda I x equals to 0. Now since in the definition here I am talking about X is a non-zero matrix. X is a non-zero vector, or it is a non-zero matrix. So if X is non-zero, since X is not equals to 0, it means A minus lambda I. It means A minus lambda I is singular, so that mod of A minus lambda I, or determinant of A minus lambda I equals to 0. Okay. Now let's proceed to a problem in which we have to find eigenvalues and eigenvectors for any matrix A. So let's find out the values, or find out the eigenvalues and eigenvectors for a matrix A, and let the matrix A is, the matrix A can be written as it is given as 3 1 4 0 2 6 0 0 5. So first of all we have to find out A minus lambda I. We have to find out A minus lambda I. So as because A minus lambda I equals to 0, that means it will be 3 minus lambda. So this is the first term will be 3 minus lambda, then 1, then 4, then 0, then 2 minus lambda 6, and then 0 0 5 minus lambda equals to 0. Sorry, it will be determinant. Now we have to expand this determinant. It will be 3 minus lambda into 2 minus lambda into 5 minus lambda equals to 0, as because the other terms are 0. So therefore, we have find three values of lambda as 3 minus lambda equals to 0, from which we get lambda equals to 3, lambda equals to 2, lambda equals to 5. Let it be written as lambda 1 equals to 2, lambda 2 equals to 3, and then lambda 3 equals to 5. So these three values are actually the eigenvalues of A. So up to this, we have already find the values of the eigen values of lambda. That is, we have already obtained the eigenvalues of the matrix A. Now let's move on to the eigenvectors. How to find the eigenvectors? That is, now we have to find out the value of capital X, as because capital X is the eigenvector. To find capital X, again we have to, let's remove all these things, just have these values of lambda. Now for lambda 1 equals to 2, so here we have obtained three eigenvalues, and for each eigenvalue you have to find out the eigenvector for each eigenvalue. So since there are three eigenvalues, we have three eigenvectors. So let's start with the first eigenvalue, that is case 1 or lambda 1 equals to 2. So when lambda 1 equals to 2, let the eigenvector be x1. That means we have to write a minus lambda I. So by putting lambda equals to 2, it will be a minus 2i into x1. Let it be the eigenvector, and it will be equals to 0. So a minus 2i. Now what will be a minus 2i? It will be 3 minus 2, 1, 4, 0, 2 minus 2, 6, 0, 0, 5 minus 2, and x1 is written as their elements x1, x2, x3, and 0 is also written as 0, 0, 0. I think this is not a problem for you all. So this will be the matrix reduces to 1, 1, 4, 0, 0, 6 and 0, 0, 3, and then here x1, x2, x3, and the right hand side remains the same, that is 0, 0, 0. Now from here we can write three equations. From these two matrices, that is, it will be x1 plus x2 plus 4x3, x1 plus x2, x1 plus x2 plus 4x3 equals to 0. Let it be equation 1. Then from the second row, it will be x1 into 0 plus x2 into 0 plus 6x3 equals to 0. It will our equation 2. And here from the third row, we can write 3 of x3 equals to 0. That is equation 3. Now from these two equations, that is from equation 2 and equation 3, we conclude that x3 must be equals to 0, as because from equation 2 it is shown that 6x3 equals to 0, and from equation 3 it is 3x3 equals to 0. So it will give us x3 equals to 0. And now putting the value of x3 0 here in equation 1, we obtain x1 plus x2 equals to 0. From here we get x1 plus x2 equals to 0. Now we have no other values, so we have to put some arbitrary values. So let x1 equals to 1. If x1, so let x1 equals to 1. Now if x1 equals to 1, it gives us x2 equals to minus of 1. So here we obtain three values of the eigenvector capital X, three elements, that is x1 equals to 1, x2 equals to -1, and x3 equals to 0. And so x1, that is the eigenvector corresponding the eigenvalue lambda 1, that is corresponding to the eigenvalue 2, is written as capital X1 equals to some constant C1. X1 means 1, x2 -1, and x3 0, where C1 is a scalar quantity. So where scalar quantity is C1, where C1 is a scalar value or just a value. So that is the process, this is the process how you can find out the eigenvectors. And since we have lambda, we have three values of lambda, we have to proceed in this manner to find out the three different eigenvectors. So let's move on to find out the second eigenvector, that is the eigenvector corresponding to the eigenvalue lambda equals to 3. I think lambda 2 equals to 3, that is our second eigenvalue. So for lambda 2 equals to 3, this equation becomes a minus 3i equals to 0. This equation becomes a minus 3i equals to 0, and then after putting a and subtracting from 3i, we have 0, 1, 4, 0, -1, 6, 0, 0, 2, and here it will be x2 as we are going to find out the second eigenvector. So again the components or the elements will be x1, x2, x3 for capital X2, and here also 0, 0, 0. So from this the equations can be written as 0x1 plus x2 plus 4x3 equals to 0. So x2 plus 4x3 equals to 0. Let it be equation 4. Then minus x2, then minus x2 plus 6x3 equals to 0. Let it be equation 5. And after that, twice of x3 equals to 0. And this is equation 6. Now from this equation 6, twice x3 equals to 0 means x3 obviously equals to 0. And for x3 equals to 0, if we put this value in any of these equations 4 and 5, x2 will be 0. So we have x2 equals to 0, x3 is also equals to 0. And what will be the value of x1? As because here from these three equations there is no x1, or these three equations are actually independent of x1. So we have to again take any arbitrary value for this x1 and let it be x1 equals to 1. This is actually an arbitrary constant, as because we have not yet find out the value of x1 from this matrix manipulation. So our x2 vector will be again some constant c2, then x1 1, x2 0, and x3 0. Again c2 is a scalar quantity. So we have already find out the second eigenvector, that is x2. Now let's move on to the third eigenvector, and for this lambda was 5, that was our third value of lambda, that is lambda 3. And so this main equation, it reduces to a minus 5 lambda, a minus 5i, rather a minus 5i, and this will be x3. And after subtracting this, we find the matrix as -2, 1, 4, 0, minus 3, 6, and then 0, 0, 0. And for x3, again we are writing x1, x2, x3 as their elements, and again 0, 0, 0. So here from we can write minus 2x1 plus x2 plus 4x3 equals to 0. Let it be equation 7. Then minus 3x2 plus 6 of x3 equals to 0. Let it be equation 8. And we have no other equations left. Now from these two equations, we find out that twice of x1, rather here from this equation 8, we get x2 equals to twice x3, x2 equals to twice x3, and if we put x2 equals to twice x3, twice x3 equals to x2, that means twice of x1 equals to 3x2. So that means twice x1, and that means 2/3 of x1. So x2 equals to twice x3 equals to 2/3 of x1, or twice x1 is equals to 3x2, and that equals to 6 of x3. Now we have to again take some arbitrary values to find out x1, x2, and x3, and for this let x1 equals to 1. And if x1 equals to 1, then x2 will be equals to 2, and x3 equals to no, let's take x3 equals to 1. If x3 equals to 1, then x2 equals to 2, and x1 will be 3. Yes, let's take x1 equals to x3 equals to 1. x3 equals to 1. We get x2 equals to 2, and x1 equals to 3. Yes, x1 equals to 3. So we have concluded that x3 will be, again there will be a constant c3, and now just putting the values of x1, x2, and x3, that is 3, 2, and 1, and this is the eigenvector capital X3 for eigenvalue lambda 3 equals to 5, and this is how you can proceed or how you can find eigenvalues and eigenvectors for a given matrix. Actually, this is also a big sum. This is also, you have to work out and be careful because there can be some silly mistakes, and if you have any silly mistake, then your values of these eigenvectors will be just reversed or will be cancelled. So be attentive to find out. Now we have the last topic left for this class, that is the diagonalization. Now simply diagonalization, if capital A be any square matrix, if capital A be any square matrix, and we have eigenvalues, that is lambda, we have the eigenvalues or the characteristic roots, as I have earlier mentioned, that characteristic roots are nothing but the eigenvalues. So if capital A is a square matrix, is a n row square matrix, and its characteristic roots are lambda 1, lambda 2, dot dot lambda n, then the diagonal matrix can be written as capital A equals to, it can be written as lambda 1, then 0, 0, and then put last element should be 0, then 0, lambda 2, 0. So then 0, 0, 0, and this will be lambda n. So this is how the diagonalization or the diagonal matrix can be written, and this technique is the diagonalization technique. Actually, to write a diagonal matrix or to find the diagonal matrix of A, again you have to obtain the eigenvalues or the characteristic roots of A. So let's take a problem. Say diagonalize A equals to 4. It is a matrix given as 4 by 3, root 2 by 3, then root 2 by 3, and 5 by 3. So this is a matrix given, and we have to diagonalize this matrix. So again, you have to find out the characteristic roots. So the characteristic equation, that is determinant of A minus lambda I, must be equals to 0. So you have to write A minus lambda I, determinant of A minus lambda I equals to 0, and it will be 4/3 minus lambda. The second element should be root 2 by 3. This is also root 2 by 3, and this will be 5 by 3 minus lambda, and it should be equated to 0. And here from this step, to reduce this, you have find 4/3 minus lambda into 5 by 3 minus lambda minus 2 by 9 equals to 0, or it will be 20 by 9 minus 4/3 of lambda minus 5 by 3 lambda plus lambda square minus 2 by 9 equals to 0. 4 by 3 lambda minus 5 by 3 lambda, it will be 9 by 3 lambda, that is only 3 lambda. So it will be lambda square minus 3 lambda, and 20 by 9 minus 2 by 9 makes 18 by 9, that is 2. So it is lambda square minus 3 lambda plus 2 equals to 0, or it can be written as lambda minus 2 into lambda minus 1 equals to 0, and then you find lambda 1 equals to 1, lambda 2 equals to 2. So these are the two characteristic roots or the eigenvalues. Now, as we have obtained the characteristic roots or the eigenvalues of A, so just a step to get the diagonal matrix. It is written as capital D, and let's put the values of eigenvalues, that is lambda 1 equals to 1, so it will be 1, 0, and then 0, and then the value of lambda 2 as 2. So this is the diagonal matrix capital D of the matrix A given here. So this is all about your syllabus of your PG exam regarding matrix. Okay? If you find this class helpful to you, you can subscribe my channel and please give feedback in your group. So, bye.